Howdy guys, welcome to another stats video. We're talking about combinations of random variables. Um, we have a couple probability distributions or tables of probability, events that with probabilities tied to them, and we're just going to find the expected value or mean and the standard deviation. We've done this before. We are adding these guys up. And divide by the number of them that we have. To find the standard deviation, we're going to take the square root of the differences squared, the sum of the square of the differences. Let's do the square root last. It's messy. Let's just kind of review from last time. It's going to build into this time. We divide by 4, we take the square root of that. It's 11.1803. Okay, so these were grades on a test. The teacher feels bad that nobody got 100 on the test and decides to add 10 to every grade. So if you add 10 to every grade, this is going to be 60 plus 10, which is 70. This is 70 plus 10, which is 80. This is 80 plus 10, which is 90. 90 plus 10, which is 100. Okay, the sum works the same way. Sorry, the mean works the same way. The question is, what's the effect of adding 10 to every single one of these on the mean and the standard deviation? Okay, notice this is 75 plus 10. The mean that we had up here plus 10. Down here, we're going to figure out the standard deviation again with our new mean. And our new values, test scores. Notice that these guys are the same. Even though we added 10 to every single one, and kind of the idea there is, if you think about a normal curve, if you add 10 points to all these values, that normal curve comes over, slides to the right, right? It's a transformation, a shift to the right. So the mean, the center of that guy, is moved over 10 units. But the spread doesn't change, right? So the standard deviation won't change. Another option is to multiply every grade by 1.1 because 90 times 1.1 is 99, and I guess that's close enough to 100. So what's 60 times 1.1? 70 times 1.1. 80 times 1.1, and 90 times 1.1. So we'll figure out the mean again. Notice this is 75, our original mean, times 1.1. What happens to our standard deviation? 12.2984. Notice that is 11.1803, original standard deviation times 1.1. So what can we say for rules? One way to write this is the mean, if we add c to every single x value, that's going to be the mean, the original mean, plus c. How did that affect the standard deviation when we added c, 10 in this case, to every single value? It didn't. The standard deviation was the same as the original. What about multiplying every single value by 1.1? That was the same as multiplying the original mean by 1.1. And the standard deviation, when we multiplied every single value by c, is c times the standard deviation. Okay. Let's look at this. Oh God, we're back to Dungeons and Dragons. I just thought we were done with that. Okay, we're playing Dungeons and Dragons with a lazy DM who says that, I'm not sure what that is, who says that, I definitely stole this problem, who says that instead of rolling 2 dice for a critical hit, you can just roll 1 and double the number. Are these the same? The key question is doubling a random variable the same as adding a random variable to itself? Well, we're going to figure that out. So we need to find the mean and standard deviation. You need a website to do this. One that works, not the only one that works. If you have a calculator at home, it's probably the easiest way. That's what I use. But metacomputer.com / I think that's a / statistics. That'll get you there. And in class, I'll show you how it works. And if you miss class, then figure out how it works. Or come to tutoring. So the simulation is first roll 1 6-sided die 30 times and double each result. So you have to write those down somewhere. Calculate the mean and standard deviation of your rolls using your calculator. Well, this thing. Right. So I did that. My original mean was 3.7. And 1.6575. So if I double that, I end up at 7.4. And oops. Why double it? Well, that's what we're talking about, right? We're doubling each result. We know if we double each result, if we multiply each result by 2, it's the same as multiplying the mean by 2 and the standard deviation by 2. Okay. Then roll 2 6-sided dice and calculate the sum 20 times. So I'm going to do this first roll and second roll, where the x's are the first sums, first rolls. And y are the second sums. So I got 3.25 and 1.6819 and 2.55 and 1.5035. So the question is, what happens when we add these together? We get, excuse me, it's 5.8. question also is, what's the standard deviation? So you might think that if you added if you add these guys together, these means together, you should get the average of x plus y. This should be this, guys. And you do, but you might think that if you added these guys together that you ought to get this, and you don't. So there are rules for this. You're fine. There are rules for this that we need to talk about too. So the mean and standard deviation double in the first simulation. If you hear rattling in the background, the dog's getting a treat. And then mean is the sum of means, but the standard deviation is not the sum of the standard deviations in second simulation. So there are rules for combining random variables, and that's what we're kind of dancing around, right? The answer is no, not exactly. The rules for this are as follows. If you want to find the mean of a sum of random variables, x and y, that's the sum of the means. And that's what we expect, and it's pretty straightforward. Also, the mean of the difference is the difference of the means. So yay, that works the way we want it to. The only thing that's a little bit exciting is the standard deviations. So the standard deviations aren't the sum of the standard deviations, but the variances. Remember, variance is just standard deviation squared. So the variance of the sum is the same as the sum of the variances. So if you had these standard deviations, you could square them. I haven't checked to see if this works, but it ought to. And if you sum these variances together, it ought to give you this guy squared. And I don't have time to do it. I'm going to run out of video time, but that should happen. So the same thing works for the differences of variances, except, and it's kind of weird, remember we're talking about change and spread. So even though you're finding the variance of the difference, it's the sum of the variances, which is kind of weird. Now we don't have one of these problems examples. We just wanted to show you that because you're liable to see that on in future classes for statistics. Let's see. Got 45 seconds left in this video. I don't think there's any way I can finish it on this particular take, so we'll have two videos. Tune into the next video for the last little piece of these notes, this problem number 1.